take his scale model to a special test site.
What we're going to do is carry out a test for stability on a specially designed scaled-down model, because I was really concerned with what we found in the Dominican Republic.
The test will take place in one of the biggest wind tunnels in America.
Wow, that is a big fan.
A 4,000 horsepower motor drives the colossal 13-meter fans so fast they generate winds as high as 217 kilometers an hour, the speed of a Category 4 hurricane.
So that's the rig.
Yep.
We're going to suspend our model of the balloon from there and allow it to move as it pleases to get kind of a feel for how it behaves in moving air.
What we don't know is whether it's going to be stable. We've got our fingers crossed to see it work well.
Fred's fiberglass model is 1/20th the size of the final prototype. The goal is to check its aerodynamics at different wind speeds. For the test, it'll hang upside down.
This is an inverted test. So we're going to use the weight of this model to act as if it was the buoyancy of the helium.
The first test is a control. Fred wants to show Basil the challenges in making the turbine stable.
As the wind comes up on this, I expect to see this actually not work. This would be like a plane without a tail rudder.
So what you're saying is that this test will give us a very good idea of what we'll need to do to make this stable.
Absolutely.
As the propellers start spinning, Basil and Fred watch the results on control room monitors.
What's the wind speed now?
Increasing speed to 20 miles per hour.
When the speed is raised to 48 kilometers per hour, the prototype loses all stability.
This is what I expected would happen. It's totally out of control.
The model gyrates as it simultaneously spins from end to end. But to generate electricity efficiently, the turbines must rotate broadside to the wind. Fred knows the only way to make that happen is with a rudder. He's designed a rudder for the turbine consisting of 3 discs. If his calculations are correct, they should keep the length of the aerial turbine at a 90-degree angle to the wind.
The rudder-like discs will act like a weather vane and cause it to orientate itself into the wind flow.
Right, so let's do number 2 experiment.
Yeah.
With discs. So these fins are going to act as a weather vane and keep it in the correct orientation.
Yes.
Going to 20 miles per hour.
You've got to admit, that's not looking good.
No, it's not looking good at the moment.
The failure to stabilize catches Fred off guard.
Did you expect to see that?
Well, no, I was expecting to see some level of stability from the discs.
But he thinks he knows what's wrong.
We have a problem at the sides of this. The wind is causing a very strong oscillating effect. So we've got to overcome that.
The configuration is flawed because the outer fins force the air over the edges of the balloon, causing uncontrollable horizontal spinning. Fred's solution is to remove the outer discs and leave only the center one.
What I want to do in this test is use the single disc, the center disc. If we're correct, then we've learned something, which is that the 2 outer discs are a problem and the inner center disc is not a problem.
What I'm going to do now is take a smoke wand in. That's going to enable us to see exactly what the wind is doing.
Well, certainly hope this works.
It's a big improvement.
Yes, that's good, that's good.
At 48 kilometers per hour, the model is relatively stable and remains in the correct orientation. So they increase the wind speed.
Basil, I can see the smoke breaking away at the ends. We've got a problem there.
Definitely see quite a large twisting force, Fred. It looks like the wind is just going around the end pieces. It's kind of being pulled right. Now it's being pulled left. Now it's being pulled right.
That's not a good thing.
One disc gives the airship stability, but only in low-speed winds. When the airflow rate is increased, the wind is redirected unevenly off the ends, pushing the airship from side to side.
Stopping test.
We've got a problem. We have not got aerodynamic stability.
Basil knows if they can't come up with an effective design soon, he'll be forced to pull the plug on the entire project. All he can do is push Fred to work harder on his dream.
Let's take everything that we've learned today and use it to come up with a solution to this challenge.
Days later, at his airship research facility, Fred meets with Jennifer Languel, the team's engineering specialist.
So, what solutions did you come up with to stabilize the balloon?
What we've done, quite simply, is we've changed the style of the blades so that they bring the load to the center and cause a stability by peaking that load. And that's done by creating chevron blades.
The turbine's new chevron-shaped blades guide the wind along tapered edges to a central disc, or stabilizer. Because the flow is directed to the midpoint, the airship should stabilize. At least, that's the theory.
So what we're doing is, instead of having all the force evenly distributed across here, really making it so that we have a stronger force in the middle.
Yeah, we're grabbing that and bringing it into the center.
The generators should get the most energy out of the wind, because the chevron blades keep the airship broadside to the wind.
In my judgment, I think that we're ready to basically go to prototype.
While Fred's crew assembles the material for the airship's outer skin, the team tackles the next big engineering challenge: the tether that will anchor the turbine to the ground.
The tether is the most important component of this system. Not only does it need to be strong and lightweight, it needs to conduct electricity, and it seems to be one of the biggest engineering challenges we're facing right now.
The design demands are extreme. The tether has to be light enough to let the airship rise to the target altitude, conductive enough to transfer electricity to the ground, and strong enough to handle at least 5 tons of pressure and weight without stretching or breaking. That 5-ton load requirement equals the weight of 5 mid-sized cars. And that inspires Jennifer to create an innovative experiment to evaluate materials for the tether.
All right, bring it in!
They'll test 2 competing tethers by using them to lift a string of cars, each weighing a ton. The stress should replicate 5 tons of drag acting against the turbine.
So what we're here to do today is basically check both the strength and the conductivity of our tether. In order to get the load that we need, I know we need to lift 5 cars.
Jennifer will test a high-quality steel cable first. Then she'll test a tether made of a futuristic material called Vectron, one of the toughest plastics on the planet. To create it, the team has brought in microfiber engineer Jeremy Lawson.
Vectron has a great strength-to-weight ratio. Other materials that are as strong, like steel or other metal alloys, just weigh way too much. We had to use a fiber, and Vectron was the best option.
The molecular chains of conventional plastics are random and tend to stretch. Vectron molecules form in highly ordered chains, giving the plastic exceptional strength and stability. Over 500 strands of Vectron will be woven together to form the core of the tether.
It's super lightweight, it's super strong, and to transmit the power, you really need something that doesn't have a lot of elongation.
Since Vectron can't conduct electricity, copper wire must be wrapped around the tether to transmit power from the turbine to the ground. It's a revolutionary but untested design.
We've never tested the entire system in conjunction with the copper wire. It's very much a prototype.
The cars for the comparison test will first hang from a 4.5-meter section of steel cable, then from a 4.5-meter length of Vectron tether.